Right. The lesson today is assignment problems using Hungarian algorithms. Yesterday, I have actually shown you how to solve assignment problem based on bipartite graph. Today, you should be able to derive an adjacency or cost matrix for a table, understand what Hungarian algorithm is, and be able to solve minimizing assignment problems using Hungarian algorithms. We will talk about maximizing tomorrow, but today we are going to concentrate on the word minimizing. Now, what actually is Hungarian algorithm? The Hungarian algorithm is used to find the minimum or maximum in assignment problems. The algorithm can solve the assignment problem without having to list all possible allocation. Remember yesterday, when we look at the bipartite graph, you actually have to list all possible allocation. In this case, you do not have to. This algorithm applies to an n by n matrix. Now, I want to stress that n by n matrix, i.e. a square matrix, to find an optimal solution to an assignment problem. So, let's look at how to solve assignment problems with Hungarian algorithms. Now, let's think about minimizing using the Hungarian algorithms. Alright? First, you need to identify n by n square matrix, or the cost matrix, or the adjacency matrix. Alright? Then, you need to subtract the smallest entry in each row. So we call this a row reduction. Alright? Of the matrix from all the entries in its row. Then subtract the smallest entry in each column. We call this a column reduction of the matrix from all the entries of its column. Draw as few horizontal and or vertical lines to cover all the zero entries. Now, let's have a look at step 5. There are 2 steps to it. If the minimum number of lines covering the zero is n, highlighting the word n, that is the same as the number of rows and columns of the cost matrix, then an optimal assignment is possible. From 5a, you proceed to step 7. If not, if the minimum number of lines covering the zero is less than n, highlighting less, an optimal assignment is not yet possible. So you need to proceed to step 6. Then you need to find the smallest uncovered, again highlight the word uncovered, entry, then subtract, highlighting that, it from all uncovered entries. Then add the smallest uncovered entry to all entries that are covered twice by the horizontal and vertical lines. Then you repeat step 4 and 5. And then if everything goes out well, you can go to step 7 with choose. Then you can choose a combination in the table that gives 1 0 in each row and column. Then you can calculate the minimum cost. Now, when you're doing step 7, the hint is first consider the row or column which have only 1 0, as that entry must be chosen. Alright? Now, let's go on to an example. Example 1. Let's consider the situation where there are 3 workers A, B, and C who have to complete 3 jobs, 1, 2, and 3. With only 1 job being assigned to each worker. The table shows the time taken by each of these workers to complete the jobs in hours. Alright, let's think about that. That's hours, that's a unit. Assign workers to jobs such that each worker is assigned a different job, and then the total cost or the time taken is minimized. Alright, now you did have a look at this problem yesterday using a bipartite graph. This time, what I would like all of you to do is identify the adjacency matrix or the cost matrix. Alright, so basically the cost matrix are just all this number here, and we can write that. So 833546253. So it is a 3 by 3 matrix. Alright, so now let's solve using Hungarian algorithm. Step 1 is identify cost matrix. You have done that. Step 2, let's do the row reduction, which means you got to deduct the smallest entry in each row of the matrix from all the entries of its row. So if you look at the first row, the smallest entry is actually 2. So this column, this number here will be 8 minus 2, which is 6. And then this will be 5 minus 2, which is 3. And here will be 2 minus 2, which is 0. Alright, let's have a look. Second row, that is the smallest. Third row, it doesn't matter. 3 is the smallest. So you can use either one. And what happened is, once you have done the row reduction, this is what you get. This is 6 is actually 8 minus 2. 3 is 5 minus 2. 0 is 2 minus 2. Alright? Same with the next row. 3 minus 3 is 0. 4 minus 3 is 0. Is 1. 5 minus 3 is 2. And so on and so forth. Once you have done that, what I would like all of you to look at now is actually the column. Let's have a look at the column. Alright? So here, what is the smallest number? Is 0. Smallest number is 1. Smallest number is 0. So therefore, do the same thing as the row. What we need to do is subtract the smallest entry in each column of the matrix from all the entries of its column. Alright, so therefore 6 minus 0 is 0. 6 minus 0 is 0. Alright, this 2 will be 0. This will be 3 minus 1. 1 minus 1. This is 3 minus 1. 2 minus 0. 2 minus 0. Alright, next bit, we need to draw as few horizontal or vertical lines to cover all the 0 entries. Let's have a look at this. So you could possibly do that because there are 2 zeros in that row. Next line, another 2 zeros, and then finally we've got 1 0 left, which is not covered. Let's do a column. Alright, if you liked, we could actually do it this way as well. 6 0 0 2 0 2 0 2 0. We could actually look at the first one, which is here, crossing out to 0, crossing out to 0, and crossing out 1. So you actually do have 3 lines, whether it's 2 vertical line or 2 horizontal line, it really doesn't matter. Alright, so now number of lines is 3, therefore optimal solution is possible. Let's have a look. We rewrite this matrix and we can choose the 0 from the matrix. We're going to start off with looking through row 1, row 2, row 3. Row 1 has got 1 0. So you know that we must pick this 0. Alright. Once we pick this 0, alright, which means A must be assigned to 3. We cannot assign this 1 to person 3 anymore. Therefore, you need to assign this to person 3. Alright, which is C. And then, because we have assigned 1 to 3, we cannot assign this anymore. So B has to go to 2. Alright? So, this is how you actually look at the optimal solution. You start off with the row or the columns with 1 0 first. Alright? You could have easily start from column first, which means column 2 first, which means you'll find your 0 here. So if I use a different color, so if I start off with column, I'll do this first. Alright, therefore I cannot assign 2 to anyone else. Now once I've assigned 2 to B, cannot assign 1 to B, I have to look at the next one, which is C. Once I've assigned to C, I cannot assign number 3 to C, therefore 3 will go to A. So either way, that's fine. Look at the column first or look at the row first. Now, therefore, the last step tells us how we can allocate a job. So we allocate workers A to job 3, which is 2 hours. You need to refer back to this table, 2 hours. And worker B to job 2, 4 hours. Again, this refer back to the table, and then 3 hours, which is worker C. So think about it, you can use Hungarian algorithm instead of writing out every single combination. In this case, you can see that the total hours is actually 9 hours. Of course, if you like, you can actually draw the adjacency matrix. All right, which not adjacency matrix, the bipartite graph. So you've got A, B, C, and job 1, 2, 3. So A is assigned to 3, B is assigned to 2, C is assigned to 1. All right, so that's if you need to draw a bipartite graph. Now, let's have a look at example 2. This time, I want you to think about 4x4 matrix. A publishing company has 4 delivery jobs to 4 clients. The cost of each delivery job with each company is shown in the table below. Allocate these delivery jobs such that each courier company gets one of the job and the total cost to the publishing company is kept to a minimum. Alright, we again did look at this example yesterday, but we actually listed out all the possible combination. This time we are not. What we're going to do is actually do a cost matrix or an adjacency matrix, which is from this table. So rewriting that into a table form, you have situation like this. Column 1, 140, 100, 40, and 200. Column 2, 100, 180, 180, 140. Column 3, 80, 140, 110, and 60. And column 4, 110, 60, 60, and 140. Alright, now, let's start off with the row reduction. First row, what is the smallest? 80, correct? Second row, 60. Third row, 40. And the last row is 60. So row reduction, you use all the numbers in that row, take away the smallest number, which is 140 minus 80, 100 minus 80, and 80 minus 80, and 110 minus 80. So if you do the row reduction, this is what you'll get. 140 minus 80 will give you 60. 100 minus 80 will give you 20, and so on and so forth. Now, take some time, think about what I have done. Alright? Here, the next bit you need to look at is then the column. So, with the column, I'll use a different color. What is the smallest in column 1? 0. Smallest in column 2 is 20. Smallest is column 3, 0. Either one doesn't matter. Smallest is column 4, 0. Alright? So let's do the row reduction. So basically, if that's 0, everything will remain the same. 140 minus 0 is 0. 40 minus is 140. 40 minus 0 is 0. 60 minus 0 is 0. And so on and so forth. So the column reduction will form a matrix like this. A 4x4 matrix. Alright? 640, 0, 140, 0. Because that is 20, take away 20. 120, take away 20. 140, take away 120, which is 120. And 80, take away 20, which is 80. So now, what can you do? You've already done your row reduction. You have already done your column reduction. You need to now cross out the 0. So let's have a look. What can we do? Alright. Cross out the first one, which is 2 zeros there, and then I cross out there. And then I cross out this and that. So therefore, I've got 4 lines. Of course, if you like, you could have done it all vertical line as well. So I'm going to show you if I write this at 60, 40, 0, 140, 0, 100, 120, 60, 0, 80, 70, 0, 30, 0, 20, 80. Alright, if I don't start off with rows, I want to start off with column. I can actually do this column first to 0. That's fine. Another column, another column, another column. You covered all to 0, and therefore you know you have achieved the optimal solution. Of course, you can do 4 horizontal lines as well. That's nothing wrong with that. So just make sure that you do not double cross, as in you do not cross here, and then you do not cross. I will highlight this, cross this one, and then cross this one again, because there's only 1 0 here. You're crossing 1 0. All right, here it's okay, because you cross out 1 0, you need to cross out another 0. So that is fine if you do it that way. All right, so since there are 4 lines, there can be an optimal solution. Let's have a look at rewriting this matrix without the line. All right, without the crossing. So now, what are you going to do? Look at the rows or the columns with 1 0 first. So if I look at the rows, straight away I know that I need to assign courier B to column 4, courier C to client 1, and courier D to client 3, because there's only 1 0. Now, since I've assigned courier D to client 3, I cannot assign client 3 to courier A. Therefore, I have to assign client 2 to courier A. Alright, so now we can work out the allocation. A to 2, B to 4, C to 1, and D to client 3. So you can work out the total cost, which is 260. Alright, sometimes there are questions, people ask me, can I do the row reduction first? The column reduction first before the row. Generally, I prefer you to do the row reduction before the column reduction. However, it is alright if you do the column reduction first before you do the row reduction. That is fine. But remember one thing, stick with what you know, which is, let's do row reduction first. Now, the next one, you've got 4 jobs and 4 workers. Can you show can you actually use Hungarian algorithm to minimize the total cost of this assignment? Of course, the first thing you need to do is always your cost matrix. Alright, write that out. That's your n by n, which is a 4 by 4 matrix. Now, let's have a look at the minimum. That's 7. Here is 25, 7, and over here is 20. Alright, so doing your row reduction, 30 minus 7, 34 minus 7, 12 minus 7, and 7 minus 7, of course. Alright, it will become this matrix. And next, we need to think about the column reduction. So in this column, this is the smallest, 0 is the smallest, 0 is the smallest, 0 is the smallest. So now, let's work out the column reduction. And you've got this. Let's see if you could actually draw a line. Now this time, draw the lines. This time you got to be really careful. Alright? You can't do this, because what you're looking at is, I can draw a line to actually cross out the 2 zeros. So therefore you must not do that. You must not do the vertical line. You have to do the horizontal line first. Alright, and then you should do this, which is cross out vertical line, cross out to 0, and then you could do either horizontal with 1 0 or vertical with 1 0. That's fine. So the way I've done it is this way. So it really, as long as you know that there's 3 lines, that's it. Alright, now what's the issue here? The issue is now we have only 3 lines. We don't have 4 lines. Alright, so what do we need to do? Let's have a look at your Hungarian algorithms let's go back and have a look at your minimization, process of minimization. Alright, here is 5b. If the minimum number of lines covered the 0 is less than n, an optimal assignment is not yet possible. Go to step D. This time you need to find the smallest uncovered entry and then subtract it from all uncovered entries. And then add the smallest uncovered entry to all the entries that are covered twice by the horizontal and vertical line. So if let's go back to this slide here. We go back to this slide. We can see that the smallest uncovered is actually 5. Alright. So what we need to do is operate on the uncovered number first. Alright. So 24 minus 5, 27 minus 5, 7 minus 5, 11 minus 5, and 10 minus 5, and 5 minus 5. So you come up with the uncovered numbers. Then what you need to do is add 5 to this, the number that's covered twice. Alright, so therefore what you get is 24 minus 5 is 19. We don't touch any of this because they are already crossed out, except those crossed out by cross out twice. So if it is crossed out 1, we just leave it. And then 27 minus 5 is 0, and 5 minus 5 is 0. Then the second line, 7 minus 5 is 0. Don't touch the 0. 11 minus 5 is 6. And 5 minus 5 is 10 minus 5 is 5. Do not touch this. And 25 plus 5 is 30. Don't have to worry about the 3 or 0. Don't worry about the 9. 1 plus 5 is 6, 0, and 11. Now, let's cross out the 0. Of course, let's do the double 0 first, which is horizontal and vertical. And then we've got that and that. Could be horizontal, could be vertical, doesn't really matter. Now, you see that you've got 4 lines, and it's a 4 by 4 matrix. Therefore, you can obtain an optimum solution. Rewriting this, you will get this matrix here, and allocating B to job 2 because there's only 1 0 there, D to job 3 1 0 there, and we know that once we allocated job 2 to worker B, we cannot allocate job 2 to worker A. So therefore, A will go to 4, and then C will have job 1. And you can work out worker A to job 4, worker B to job 2, worker C to job 1, and worker D to job 3. The total cost is 12 plus 25 plus 15 plus 20, which is 72 units. Alright, this is actually Hungarian algorithms. Let's just recap. We are doing the minimizing. So you must always identify the n by n square matrix. And then the row reduction, the column reduction. And then draw as few horizontal or vertical lines to cover all the zeros entry. So if the minimum number of lines covering the 0 is n, which is the same as number of rows and columns of a cost matrix, then an optimum assignment is possible. Go to step 7. If not, go to step 6. So what you need to do is find the smallest uncovered entry, subtract it from all uncovered entries, and then add this to the covered entry, which are covered twice by the horizontal and vertical lines. Then repeat step 4 and 5. Generally, after one iteration, you will be able to go from 5A to 7. Alright, there's very occasional that you may have to go 5B again, do 6 again, and then repeat it, and then you'll get a then you can go to 7, step 7. Alright, that is the lesson for today, and you should understand how you could derive an adjacency or cost matrix from a table, understand what Hungarian algorithm is, and be able to solve minimizing assignment problems using Hungarian algorithms. Tomorrow, we look at maximizing. Maximizing is basically the same as minimizing, but there's just one extra step. All right. Same with unbalanced, which means if I've got 3 workers and 4 jobs, there's 1 extra step. That's all. All right. I'm going to stop here. Thank you for listening.